Welcome to Day 6, Reciprocal Functions, Part 1. These are the supplies that you will need. Notice you do not need a calculator for this lesson. Today we're talking about rewriting reciprocal functions. And when I say rewriting reciprocal functions, I mean rewriting them in terms of sine theta and cosine of theta. First, let's review what our reciprocal functions are. You have the cosecant of theta, you have the secant of theta, and you have the cotangent of theta. Each one of these is equal to a reciprocal trig function. Cosecant of theta is equal to 1 over sine theta, secant theta to 1 over cosine theta, and cotangent theta to 1 over tangent theta. What you notice as well is that cotangent theta and tangent theta are not in sine theta and cosine theta yet. Well, we can change this. We can write tangent of theta as equal to sine theta over cosine theta, and cotangent of theta as the reciprocal of that, cosine of theta over sine of theta. The next section proves that tangent of theta is equal to sine theta over cosine theta. Skip this section to see the examples. Okay, so how can we say that tangent of theta is equal to the sine of theta over the cosine of theta? Well, using a little bit of algebraic manipulation and some of our basic knowledge, we can figure this out quite easily. Let's start with a right triangle. We have our right angle down in the corner, and we have a given reference angle we're going to call theta. We're now going to label this triangle with the hypotenuse, the opposite side across from theta, and the adjacent remaining side. We know from our trig ratios that the sine of theta is equal to the opposite over the hypotenuse. We also know that the cosine of theta is equal to the adjacent over the hypotenuse. Finally, we know that tangent of theta is going to be equal to the opposite over the adjacent. If I look at the cosine of theta, I can easily take the reciprocal 1 over cosine theta and say that its ratio is equal to the hypotenuse over the adjacent. Now, I'm going to set up a hypothetical. I'm going to multiply sine of theta to 1 over cosine of theta. Notice I placed sine of theta over 1. If I multiply this together, I come out to a proportion of sine theta over the cosine of theta. And now another way to look at this is we know that sine of theta is equal to the opposite over the hypotenuse. We also know that 1 over cosine theta is equal to the hypotenuse over the adjacent. So with a little bit of rewriting, we multiply these two functions together. The h's cancel each other out, and we're left with a ratio of opposite over adjacent. What do you notice? Haha! This is also equal to the tangent of theta. So if we erase everything that is in between, you notice that the sine of theta over the cosine of theta lines up pretty nicely with the tangent of theta. And there you have how the sine of theta over cosine of theta is equal to your tangent of theta. And as we know, cotangent of theta is going to be the reciprocal. Thus, we can say that cotangent is equal to cosine of theta over sine of theta. In these examples, we're asked to write each expression in terms of sine theta and cosine theta, so this means we're going to have to rewrite the reciprocal functions. We know that secant of theta is equal to 1 over cosine of theta, and we're going to keep the operation between the two, in this case, multiplication. Then we rewrite cotangent of theta as cosine of theta over sine theta, which we learned from the previous example. The cosine of theta cancels out in the numerator and the denominator, and we're left with 1 over sine theta when we multiply through. This is our answer. In example 2, we notice we have the tangent of theta over the cosecant of theta. To avoid confusion, what I'm going to do is rewrite this problem so that it appears linearly. I'm going to say tangent of theta, and I'm going to write a old school division sign. And I'm going to say tangent of theta divided by the cosecant of theta, because remember, your fraction bar is the operation division. Tangent of theta, we know, is equal to sine of theta over cosine of theta when we rewrite it. We're going to rewrite cosecant of theta as 1 over sine of theta. And we're going to keep the operation in between. Now remember, when you are dividing fractions, you need to use keep, change, flip. In other words, keep the first fraction, change your operation from division to multiplication, and flip your second fraction. In this case, 1 over sine theta becomes sine of theta over 1. If you multiply the numerators through, you get sine of theta times sine of theta. Now this can be rewritten as sine squared theta, telling us that is the square value of sine of theta. So sine of theta times sine of theta is rewritten as sine squared theta, and cosine times 1 in the denominator is cosine of theta. In example 3 and 4, we're going to use the same process. I would like you to focus on thinking about the steps to solve these particular problems. First, we have cosecant of theta over the secant of theta. First off, rewrite your problem so that it appears linearly. Write the cosecant of theta, keep your division sign in between, and then rewrite secant of theta. Now we're going to rewrite our functions in terms of their sine and cosine. Cosecant of theta can be rewritten as 1 over sine of theta. Secant of theta can be rewritten as 1 over cosine of theta. Once again, we're now going to use keep, change, flip. I keep the first fraction, 1 over sine theta. I change my operation from division to multiplication, and I flip my second fraction, cosine of theta over 1. When I multiply this through, the numerator is cosine of theta, and the denominator is sine of theta. Same thing with example 4. Rewrite it so that it appears linearly. Secant of theta divided by the cotangent of theta. Next, rewrite your problems in terms of sine and cosine. Secant of theta is equal to 1 over cosine of theta. Keep your operation of division. Cotangent of theta can be rewritten as cosine of theta over sine of theta. Once again, keep, change, flip. Keep your first fraction, 1 over cosine of theta. Change your operation from division to multiplication, and flip your second fraction, sine of theta over the cosine of theta. Multiply through, and in the numerator you should get sine of theta. And in the denominator you have two cosines multiplied together, so you have a cosine squared of theta. Now we want to determine in which quadrant the reciprocal trig functions are positive. To do this, we think back to our original trig functions and how we determined which quadrants they were positive in. Remember that we used the mnemonic add sugar to coffee, ASTC, which we placed in quadrants 1, 2, 3, and 4 respectively. What this told us was that in quadrant 1, all of the trig functions were positive. In quadrant 2, sine was positive only, which meant that tangent and cosine were negative. In quadrant 3, tangent is positive, but sine and cosine are negative. And in quadrant 4, cosine is positive, but sine and tangent are negative. So you notice that there are two quadrants in which each function is positive. Our reciprocal trig functions happen to be positive in the same quadrants as their given trig functions. So in the first quadrant, all of our reciprocal trig functions are positive. In the second quadrant, the cosecant of theta is positive. In the third, cotangent is positive. And in the fourth, secant is positive. Notice that our reciprocals line up with their original functions in their quadrants. Now let's solve a couple of examples. In example 5, we're asked to find which functions are positive for angles terminating in quadrant 2. I suggest that you start by labeling your quadrants 1, 2, 3, and 4, and then using your mnemonic, add sugar to coffee, to label where your trig functions are positive. Next, label the quadrants where the reciprocal trig functions are positive. Cosecant in 2, cotangent in 3, secant in 4, and of course all of them in quadrant 1. Now, this question asks us to find which functions are positive for angles terminating in quadrant 2. What does it mean for an angle to terminate? Well, it means that the terminating side of the angle will be in the quadrant that is given. In other words, if you open an angle in standard position, its terminating side will be in quadrant 2. What you notice is that in quadrant 2, the sine and the cosecant are positive. So we can say that sine and cosecant of theta are positive in quadrant 2. In the following examples, we're asked to find what quadrant theta lies in, or rather, what quadrant the terminal side of theta lies in, based on the functions of theta and the information we already know. Let's take a look at example 6 first. I'm going to start by drawing my 4 quadrants and then labeling them. You can label them 1, 2, 3, 4. I'm also going to label them with my mnemonic, add sugar to coffee. We know that the tangent of theta is less than 0. Well, this tells us that tangent of theta must be negative. I know that tangent of theta is positive in 3 and positive in 1, so it cannot lie in quadrant 1 or 3. Next, I'm going to label my quadrants where the reciprocal functions are positive. All of them are positive in 1, cosecant in 2, cotangent in 3, and secant in 4. I know that the cosecant of theta is greater than 0. This tells me that the cosecant is positive. Since cosecant is negative in 4, I can cross it out, and I'm left with quadrant 2. In example 7, I'm going to start the exact same way. Draw my 4 quadrants and label it with my mnemonic, add sugar to coffee. Here, instead of having theta, I have an angle A. Notice I have a cosecant, so I'm also going to label where my reciprocal functions are positive. I'm told that the secant of my angle A is less than 0. This means that the secant is negative, so it cannot be in quadrant 1 or 4 where the secant is positive. Next, I'm told cosecant of the angle A is less than 0, so cosecant is negative. Since cosecant is positive in the first quadrant, I can cross that out, and I'm left with quadrant 3. In example 8 and 9, I'm doing the exact same thing, except I have to interpret the data based on different values for my functions. Start the same way, label your quadrants, use your mnemonic, and label where the reciprocal functions are positive. Now I'm told that sine of x is equal to negative 2/3. Well, what does this tell us about the sine of x? Can you see? Well, sine of x is negative, which means that it cannot possibly lie in quadrant 1 or quadrant 2. We're also told that the tangent of x is less than 0. In other words, tangent is negative. Therefore, we cross out quadrant 3, and we're left with quadrant 4. In example 9, we do the exact same thing. Draw my quadrants, label them, add sugar to coffee, and label where my reciprocal functions are positive. Here, tangent of theta is equal to 2.7. In other words, tangent is positive. So we can cross off 4 and 1 because tangent is negative in those quadrants. Next, we have cosecant of theta is less than 0. In other words, cosecant is negative. Well, if cosecant is negative, then it cannot possibly be in quadrant 1. Therefore, we're left with the only place for it to be in quadrant 3. So in conclusion, here are the skills that you should be able to do. If you're having trouble with any of these skills, go back and rewatch the video and pay special attention to the skill that you think that you are weakest in. Until next time, this is Mr. Mackman signing off.